to Module 52 on graph theory, nodes, edges, and clustering. This is going to be very, very high level today. So there's a lot of text for pretty simple learning outcomes. We want to just basically be able to conceive of relational data, that's data with relationships between data points, as a graph. And this is normally considered visually in terms of nodes and edges. We'll be able to distinguish between different types of graph. We'll define each of them. You'll be able to compute and interpret degree and neighborhoods. This is basically some statistics about relationships between adjacent nodes. You ought to be able to explain and compute the clustering coefficient, compare graphs with similar degree but different structure. Sometimes the statistics hide topological differences. And you'll be able to recognize randomness and structure in networks. Each of these topics have a very deep amount of topics we can get into, but again, today is going to be a little bit just introductory. So far, most of our data sets have been tables, where the rows have been cases or data points, customers, patients, days, and the columns have been features, like age, income, readings, and so on. And occasionally, recently, one of these columns is also our output variable. We're trying to do supervised learning. We've seen logistic regression. We've seen regression. We've seen k-nearest neighbors. So sometimes that's the last column is the label or the output. So we have used clustering already to group similar rows together that don't have these labels. We've seen things like KNN to find local neighborhoods for prediction. So both of these involve relationships. If we're clustering with k-means and classification with k-nearest neighbors, we had measurements of distance between points. This is crucial. We talked a lot about L1 and L2, Euclidean distance, the Manhattan distance. But some problems are about kind of higher level relationships that go beyond just the mere distances between the vectors representing these data points. So we might want to know whom emails whom, who follows whom, which roads connect which intersections, and so on. And sometimes for vast categories of data, just expressing things in terms of graphs makes more sense. So graphs are a way to model deep structure between things and not just features of things. And in fact, this is sort of an area of science that we want to get into because sometimes it's not just actuarial science. We care about things like causal relationships. We actually want to discover that this variable influences that variable in defined, absolute, predictable ways, or if not absolute, at least strongly predictive ways. So a graph, we call it graph G. This is a variable describing any graph, and it's defined in terms of two things. Its nodes or vertices, V for vertices, and its edges, E for edges. A node is, as the name suggests, sort of just a state or an entity. In this case, the nodes are these red circles, and the edges are the lines that connect them. And edges, for now, only connect two nodes at a time. So there's an edge here connecting A and B, there's an edge connecting B and C, a third edge connecting A and C, and so on. Each of these nodes can represent a person, like maybe it's a router in a network, maybe it's a web page, maybe it's a station. Your imagination is the limit, and there's some relationships between these things. So you can have friendship relations between person A and person C. You can have link relationships, like maybe Ethernet relationships between router A and router C, and so on and so on. Maybe there's a friendship between person A and router C, but that's not my business. So there's different kinds of specific ways that we can define edges in these graphs. So I'll just walk through the four of them now. And again, there's more than this, but this is sort of the introductory level. The undirected graph looks like this on the right here. The edges have no direction, there's just a connection between them. So the edge UV from node U to node V is the same as from node V to node U. There's no direction at all. It's not that they're bidirectional, there's no direction. So there could be mutual relationships. So if two people are friends, then there could be an undirected graph that represents that friendship, that mutual friendship. Maybe there's a road connecting two towns. There's a two-way road, and we don't need to have directions on either. Implicit here is that you could have directions on both ends, going in both directions. Maybe that's a bit more general, but to keep things simple, these edges are just, these two nodes are connected, and that's it. The directed graph, or digraph, has directions. There's an explicit beginning point and an explicit ending point. So these are ordered. So here, the edge UV does not necessarily equal VU. So UV says there is a link from U to V. In this case, A points to C, B points to C, A points to B, and that's it. You could have edges going the other direction. So just because I don't show like bidirectional relationships here, maybe I should have. You could have drawn another edge from B to A. This would be a second edge. There would be one directed edge going from A to B and a second directed edge going from B to A. Maybe this means that A and B follow each other on a social platform. A follows B, B follows A, so you have two following relationships. But it's not necessarily the case that just because A follows B, B must also follow A. So the undirected case we saw a moment ago doesn't necessarily hold. So any kind of relationship in which there's sort of a motion from one point to another is one that is naturally encapsulated within these directed graphs. A following B on a social media platform until they inevitably disengage from that platform. A links to B on the web doesn't mean B links to A. A sends an email to B doesn't mean B sends an email to A, and so on. You could have weights on each of these things. So the undirected and the directed cases can also be augmented with weights. So in the undirected weighted case, there's still no direction on the edges, but there is a sort of magnitude on these edges. There's a numeric weight. So there could be a distance. These points can be placed, these nodes can be placed visually anywhere in space, but their distance between them might be indicated by these numbers that we've attached to these edges. Or maybe there's travel time. Maybe the distance between cities is small, but in order to get from one to the other, it takes a very long time because the route is actually very circuitous, or there's traffic, et cetera, and so that amount is represented as these numbers. The strength of the connection can also be represented as these numbers. Again, your imagination is the limit. And the directed weighted is, again, the same idea. We still have a directed connection. The edges still have a direction, but now they also have a weight. So this could be like the number of messages sent from one person to another. In this graph, A might have sent person C one message, B might have sent them 3 messages, and so on. We're mostly going to use undirected, unweighted graphs for intuition, but most of what we're going to talk about generalize for each of these 4 different types of graph. And just again, there's many other types also. There's variance on nodes. There's edges that can connect multiple different points. Like we have a lot we can have at our fingertips if we want them. So for an undirected graph, like the one shown here, we define neighbors of a node V as all of the nodes U such that there is an edge UV that exists amongst our set of all edges in E. Okay, so E is our set of all edges. So here all the edges are this line, this line, this line, and these 2 lines here and here, right? So this is 5 edges in total in the set big E. So I'll define those in a moment. The degree of V, written by deg V, this is the number of neighbors. So the degree of V, this is a somewhat pedantic way of writing it, but it's important to be pedantic always because you want to be specific and correct. So if U is an element of V, so U is a node in the set of all nodes V, we have all of the edges that connect U to any V. Given V, then if U is another node in V, then if there is a connection from U, this other node in V, connecting it to V, the one I care about, and this is an edge within my set of all edges, I just count the number of such edges, so these bars represent the count, and that is my degree V. We can see an example using this graph. What are the neighbors of A? Look at A. Well, A is connected to B and C, so the neighbors are B and C. And also, because if A is V, and then U is in V. So B and C are in V, and the edge between U and V exists. This edge exists, and this edge exists in our set of edges. We count those. There's 2 of them, so the degree is 2. This is pretty simple, I hope, so far. Look at C. Well, C is connected to A, B, and D. So because edges exist in each of these connections, the degree of C is 3. Right? Just literally count the number of edges outgoing or attached to any of our edges, and that's the degree. And E over here only has one connected neighbor, which is D, so the degree of E is 1. Now, if we have all of our edges and all of our degrees, all of our nodes, each with their own individually measured degree, we can list all the degrees for all the nodes, which we're doing around here, and then we can plot a histogram. So A has 2 connected neighbors, B has 2 connected neighbors, C has 3, and so on. We can just count, we can do a histogram, so of all the possible degrees, 0, 1, 2, and 3, in this particular example. Well, one node has one degree 1. How many? 3 nodes has degree 2. That's A, B, and D. And 1 node has degree 3, which is C. A little histogram over here. Looking at things in terms of this histogram helps us to, at a glance, quickly identify if there are many leaves. A leaf is a node with only one neighbor. And in this case, it doesn't seem to be happening. There are relatively few nodes with only one neighbor. The only leaf node over here is node E. This is the only leaf in this graph. Are there a few high-degree hubs? Well, kind of. This is a very simplistic graph. It might be argued that node C is a hub. That's represented as this one over here. This degree 3 is node C. There doesn't seem to be very many hubs. There's only one of them in this case. Other distributions of these histograms might give you different understandings of the nature of the graph. So if the degree 1 was much, much higher, especially in proportion to all of the other degrees, this would indicate that this graph has a ton of leaves, a ton of nodes that only have one neighbor. If you have, maybe this histogram is a lot bigger and you have many more possible degrees, like the degrees can be much higher, 4, 5, 6, 7, and so on. And you see a lot of nodes that have high degree. Those nodes are going to be what we call hubs. They're connected to many, many other nodes, at least relatively. Those ones would be considered hubs also. So you can kind of get at a glance the overall nature of the graph by looking at these histograms. So the clustering coefficient is an important statistic. So graphs can have the same number of nodes, the same number of edges, and even the same degree distribution. So you can have a histogram like this that looks exactly the same for 2 different graphs, but the actual nature of these graphs can qualitatively feel very different. So these 2 graphs both have the same number of nodes or vertices. There's 6 in the graph. There's one graph on the left and one graph on the right. A, B, C, D, E, F in both cases. In each case, they have every vertex has 2 neighbors, as you can confirm by looking at the graph on the left and the graph on the right. But the graph on the left clearly has 2 separate clusters, whereas the graph on the left has 2 separate clusters, and the graph on the right has this kind of ring-like pattern. So we have this lattice-like graph. The idea is that our neighbors tend to be neighbors of each other. So you have each of your neighbors are also neighbors with your other neighbors. So this indicates the cliquiness of a graph. And if a graph is very random, if you imagine you have a bunch of vertices and then randomly assign edges between them, then depending on how many edges you draw, it's possible that the neighbors that you have will barely know each other. Like you have a couple of connections that have been randomly assigned to other nodes, but because of a random distribution of edges, your neighbors are not likely to be connected to each other. Okay, we'll see an example of that a little bit later on. So this local clustering coefficient of a node is going to try to capture statistics like if my friends formed a group chat. So if all the people you're connected to form a group chat amongst themselves, how many pairs in that chat would already know each other? Okay, this kind of describes this how much of a clique exists, right? How tight is your friendship network? So here we had define clustering coefficient, and this is for the undirected case. So imagine there's a node V, and it has a degree 2 or greater, right? So it has 2 or more neighbors to which it's connected. So n of V is going to be the set of all of the neighbors of V. So given V, what are all of the other vertices that it's connected to? In this set n, the number of possible edges amongst the neighbors is this quantity. This is something combinatoric, which you might not have seen before, so we're not going to make a big deal of it. But the way that we describe this visual here, there's sort of as big brackets, and then there's a number on top and a number on the bottom. And the number on top here is like the number of neighbors that node V has. The number on the bottom is 2, as you can confirm. And the way we'd say this quantity is, well, I'd say this like the amount of neighbors of V, choose 2. It's the number on top, choose the number on the bottom. And when we see this particular visual, this particular arrangement of numbers, then there's a known way that we would write it out. In this particular case, it's the top number times the top number minus 1 divided by the bottom number. It doesn't necessarily always have to be this case, but it works out to be this way for this particular combination. So what this is basically counting is, like, given the network of my friends, there could be connections between any 2 of them, and I want to count all of the possible connections between those vertices. So it's the degree of V, my neighbors, times the degree of V, my neighbors, minus 1. All of this is divided by 2. You probably saw this kind of computation several times in the past in high school when you look at things like the edges of shapes, and you look at all the possible connections between, say, a square. If you have a square with 4 edges, 4 vertices, how many possible edges exist? Well, there's like for every corner in that square, that corner can be connected to all possible other corners, and that's true of every possible corner. So you'll end up having the product of 4 times 3, but then you don't want to count each of those connections twice, so you have to divide by 2, and this gives you this quantity. So something that you've probably seen before. But this is the total number of possible edges between all of your neighbors. But in reality, only some of those edges are connected. Only some of your friends already know each other. So actual edges of V is going to be how many of those pairs in your neighbors actually have an edge in the actual graph in E. So we have this quantity down here. So for V, we have a set of neighbors of V. So for any 2 other vertices, U and W, I assume, are going to be different here. You don't have to be necessarily, but here they are. So for 2 neighbors of V, so U and W are both elements of the neighborhood of V. Count up all of the times there's a connection between U and W in my edge set. So the edge UW actually exists in my edge set. And then, given these bars on the side, just count the number of such edges. This is going to be the actual edges. It's a very long way of describing something that's very intuitive, but there we have it. The local clustering coefficient, which is what we're computing over here, is combinatoric. So just for your background, you can click on this if you want, but essentially we're looking at the number of actual edges that exists amongst the neighbors of V, divided by all of the possible edges that exist in the neighbors of V. And again, we've defined this circumstance as when V has 2 or more neighbors. If V has 1 or fewer neighbors, that means no neighbors at all, then we call the clustering coefficient 0. If this quantity is close to 1, that is to say that if the number of actual edges is very close to the number of possible edges, and then this ratio is 1 to 1, this fraction is close to 1, then this is very cliquey, right? That means, like, if all of your friends were to form a group chat, all of them would already know each other. This is a very tight clique. If this local clustering coefficient is close to 0, Like if you make a list of all of your friends and put them in a group chat, how many of them actually know each other already? Well, there were many possible friendships that existed, but none that actually existed. This fraction would be close to zero, or your neighbors would be mostly disconnected. I hope this is also pretty intuitive. So the average clustering coefficient of the overall graph, so we compute the local clustering coefficient for each vertex v. So every vertex v has this quantity c of v attached to it. We can take the average of this quantity over all of the nodes of your graph. This is the average clustering coefficient of the graph, and this kind of tells you the overall cliquiness or disconnectedness of the graph, and it gives you kind of a metric of the nature of the graph. Pardon me. This is a bit of detail that is not going to be crucial, but just quickly jump through it. If you let T of V be the number of triangles that include V, so there's we saw a couple of examples already, but there's a triangle formed of 3 nodes and edges between each of the 3 of them. If you have an undirected graph like we're talking about, then the actual edges that exist in the neighborhood of V equals T of V. So this is sort of the number of triangles that include V, these 3 cycles. Why is this the case? Every triangle through V has to contribute exactly 1 edge between the 2 neighbors of V, and you can also define the density of a simple undirected graph, with n being the total number of vertices with n nodes, and m being the total number of edges. The density of the graph is 2 times m, the size of the number of edges we have, divided by n times n minus 1. This is the overall density. We're not going to see this again really, but this is another statistic that looks at all possible edges in the graph and looks at how densely connected that graph is. This is actually often used in the real world to have a global view of overall graphs, but normally we care about local connections, and we might care about the average of these local connections. You might care about the minimum and the maximum of these also. And again, the histogram gives you a nice overview of the shape of these graphs. So you might have a histogram over the local clustering coefficients. But this is a bit of an aside. There are other statistics that describe the overall connectivity of graphs. So what are our anti-examples? Imagine we have a directed graph now. So an edge flows from U to V, means that U follows V, but V doesn't necessarily follow U in one of these ridiculous social media websites. So there's many relationships, might not necessarily be mutual. And this is indeed the case of many of these ridiculous social media websites. If you treat this as undirected, so like instead of drawing an arrow from U to V, you just draw an edge between them, and you compute degrees, clustering coefficients, and you ignore direction, then in this case you might wrongly claim, user X is very influential because they have a degree of 1,000. But it might actually be the case that this person just follows 1,000 people, and only 10 people whom they follow actually follow them back. Okay? This person is very interested in what's going on around them, but they don't have much of an influence on the world. So whether user X is influential or not is not really captured by these undirected representations of relationships that should be directed. You might also claim this community is highly clustered, right? So we might compute some of the statistics like we saw a moment ago. We might look at triangles like we quickly walked over a moment ago. But these triangles rely on edges that only exist in one direction. It's not mutually reinforcing. It's kind of you're taking the wrong conclusion by setting up the wrong graph to begin with. So whenever you're setting up a graph, like even though we're mostly focusing on undirected relationships between nodes, you have to make sure that the relationship is actually directed or undirected, and set up your graph accordingly. And then the statistics we just talked about a moment ago, those were for the undirected case. If you are actually working with a directed graph, you'll have to use the specific versions of the statistics we talked about before for those circumstances, which we're not going to get into right now. And indeed, are you interpreting degree and clustering with the correct notion of connection? So imagine there's a very small friendship network here. We have an undirected simple graph, a friend network. So if U likes V, then V likes U. Our nodes are Alice, Bob, Carol, Dave, Eve, and Frank. And our edges are AB, BC, and AC. And then we have his tail, C, D, E, and F. So C and D are friends, D and D are friends, and E and F are friends. So you may want to list the neighbors and degree of each node. You may want to compute the local clustering coefficients, C of A, C of B, C of C, and so on. And then compute the average clustering coefficient of the whole graph. This will be basically walking through an example of what we were talking about at a small amount of length a moment ago. So the average clustering is going to be the mean of these 6 quantities in step 2. So we use NetworkX. So here's a link to NetworkX to get another Python package, and we can compute these statistics. So the way that NetworkX works is we can specify graphs. So NX has this object called graph. We create the object G. Now we're going to specify a list of connections. So here we have a list defined by these square brackets, and then we have the edges here. Alice is friends with Bob. Bob is friends with Carol. Alice is friends with Carol. This, we just formed a little triangle in A, B, and C, and then we have this tail relationship. We also have this NetworkX implements in the object graph this add edges from function, which takes a list like the one we just specified, and then draws these edges from one to the other. Now we can list the nodes. And we put that in the object nodes. We take the dictionary of degree and we put that into degrees. And then we can compute the clustering coefficients. This is as simple as calling the function clustering. So those few steps of the A choose B computation we described a moment ago. This is its own function. We just run it on the graph G. And then we can produce a summary as a data frame and write it out to screen. And here we are. So Alice has 2 friends, and her clustering coefficient is 1. So both of her neighbors are already connected to each other. So the actual connections in her neighbors group is 1. The possible connections in her neighbors group is 1. So her clustering coefficient, is she has 2 or more neighbors. So it's our first possibility. Actual connections divided by possible connections is 1/1, so her clustering coefficient is 1. The same goes for Bob. Carol is connected to Alice and Bob, but she's also connected to Dave. She has degree 3, but of all of the possible connections between Alice, Bob, and Dave, there's only a connection between Alice and Bob. So her clustering coefficient is only 1/3, and then so on. Right. We can visualize this graph now. So this, we have this triangle at the bottom. This is an example of high clustering. We have this long chain at the top of low clustering. Poor Frank only has 1 friend over here. So here's just how we ended up trying it. I should mention also that NetworkX and X also has this helper function for helping us to draw such graphs, and spring layout is the function that lets us do it. G is the graph we want to draw, and seed, being the magic number 42, is sort of as a random seed that helps us distribute these nodes in space. But we don't want to specify 1 node at a time. Calling that function will help us draw this graph and determine the x and y coordinates of their placements. So the second worked example is looking at issues when we have the same degree but different clustering relationships. So we have 2 networks. Both of them have approximately the same number of nodes, the same number of edges, and the same average degree. But they have very different average clustering, and the overall structure kind of feels different qualitatively. And this can matter in some real-world circumstances. So we're going to compare the random graph, where edges are just placed independently at random. We're just going to draw connections between graphs randomly. We're also going to have this ring, possibly with some shortcuts. And statistically they'll be very similar, but they'll have very different natures. So we want to know which of these will have higher clustering. And you have an intuition about this already. You might want to jot this down if you have any intuition already. And then also which one of these might better represent a social network. One of these questions might be more intuitive to you than the other, but maybe think about it a little bit before you move on to the next few slides. So here's where we define our graphs. Again, we're going to use NetworkX. We're going to have 30 nodes. We're going to try to have about a degree of 4, a degree of 4 for every node. Then we have our random graph. Each possible edge will occur with probability p. This is going to be k, the vertex divided by n minus 1. And then we have this random thing. So Erdős-Renyi graph is a particular kind of graph which is beyond the scope of this course. We're specifying this is the number of nodes we have. This is the probability of connections between adjacent vertices. And we have a random seed. This should have been 1109, but it is what it is. It doesn't matter so much. And then we have our structured small world graph. This is called the Watts-Strogatz graph. And again, it'll draw graphs according to its own algorithm with the same number of nodes, the same number of degree, and the p equals 0 just means for this particular function that we're going to have this pure ring lattice. Same seed as before. And then we're going to summarize. We're going to just grab the degrees, grab the average degree, grab the clustering coefficients, and average them, and then summarize. And we end up with the following. The Erdős-Renyi random graph will have a degree of 4.2. We aimed for 4, we got 4.2, which is close enough for our purposes. We applied connections totally randomly, and then we have the clustering coefficients for every vertex. Taking the average of these gives us 0.12-ish. And then the ring lattice will have, by definition, degree 4, but its average coefficient will be 0.5. Let's take a look at these. These are the visual connections between them, so you can quickly count these yourself. Here's a random graph, here's a ring lattice. You can see that the structure on the right is much more organized and structured, the one on the left less so. There are connections backwards and forwards between these graphs, and you can't really see this very well, but there's kind of connections. When you draw this yourself, I'd advise you to like zoom in and out of this, and you can see that there's a lot of graphs that might not be so visible in the video between like skipped over vertices. But the one on the left is much more clearly random. So you can run this many times. You can try different seeds, and the overall shape anyway of the random graph will change on run to run. And you're going to get different statistics. You're going to see that the average degree over all of these, this first numerical column over here, will generally be very similar, but the random graph will have usually a lower average clustering coefficient, and the ring lattice will have a higher one. That's just because of how these were constructed. The ring lattice is constructed by definition to connect nodes that are relatively close to each other. So neighbors of a node will often connect to each other. Again, here you can't really see that, but the neighbors of a node will often connect to each other. And because the neighbors also connect to each other, this will increase the clustering coefficients. And then because this is true of every node in this ring, the average will also be higher. So that kind of answers the first of our questions we had a moment ago. The second of which is, well, which of these is more realistic? So looking at this, these two graphs, you might have an intuition about which is more realistic, and hopefully you've chosen the random graph. Real social networks, might actually sit somewhere between these extremes, so it's not completely random, where you're just drawing connections across all possible members of a network. But you will have sort of a random variability. You'll have cliques that are tightly connected. You'll have these sort of tree-like structures with leaves and relatively few degrees, where people are not as connected. And this will kind of occur globally with the appearance of randomness. So it won't be perfectly lattice like on the right. It won't be perfectly at random like we have defined on the left. It might be more clustered, so like the average clustering might be a good amount higher than this, but qualitatively it will resemble more or less the one on the left. So the answer to the second question is well, kind of neither of these represents a real social network, but it might be more inclined towards one rather than the other. So when you analyze networks, be they friend networks, networking networks, and so on, you have to always be sure about what your question is. If you care about load, or if you care on the routers, or you care about like traffic and intersections, maybe you're going to end up being a traffic planner for a major Canadian city. You care about degree. And therefore, there's a bunch of other statistics which we didn't have time to talk about, like betweenness centrality, that might matter most for your particular task. So again, this is just kind of opening the door to say there's a lot of statistics out there that can describe graphs, and you need to choose the right tool for the job. If you happen to care about tight-knit communities, then local and average clustering coefficients might be more relevant. So this is more or less what we talked about today. And there's various real-world circumstances in which the tight-knittedness of communities might matter to your analysis. If you care about whether vertex A is reachable from vertex B or vice versa, or what the communication speed might be between them, in that case you might care about the number, like the shortest number of connections between node A and node B. And again, that's a whole other topic where we could go several lectures on about the most optimal shortest path, like how to find the shortest path between nodes. If every edge has the equal weight, so if they're unweighted or they have equal weight connections, you'll have one solution if you care about the weightedness. So maybe like the distance or the time it takes to go from node A to node B according to this weight we apply to these vertices. A slightly different algorithm would help you find the optimum routing from those 2 points. Usually when you go into one of these online mapping tools and you say, I want to start at point A and go to point B, and I want to find the quickest way to get there in time, I want to find the shortest way to get there in distance. We have different directed edges, one with time, one with distance, and those connect all of these different intersections or points you might try to get between. And then the algorithms that I'm just alluding to right now would kind of find the optimum path between those 2 points. And it would also determine whether they're even reachable or not. Hopefully, if you try to find a bike route between Halifax, Nova Scotia and Edinburgh, Scotland, then you might ideally say, well, you won't be able to bike there directly, but here's a boat you can take across the Atlantic Ocean. So you have a checklist generally. Like you have to always remember, what does a node represent in this data set? It's just not a colored circle with a label applied to it. It actually represents something in the real world. What does an edge represent? Is it directed or weighted? What are some simple measures that support your story? We talked about degree. We talked about clustering. Those are going to be most important to us going forward. Density we touched on briefly, but only as an aside. This is sort of a global representation of how densely connected the overall graph is. And there are dozens of other measures that you might apply depending on what your circumstances are. You're going to have to ask yourself what conclusions you might draw and whether they're robust to small changes. So if you happen to remove a particular person from a graph, what would happen to your overall representation of the graph? Robustness is always important to us when we're talking about data science and machine learning. There are ethics and risks applicable to network analysis. So if the nodes in your network are people, then obviously like the conclusions you draw or the interventions you make given your conclusions will be potentially very powerful and very risky. Again, I can't really emphasize this enough about how important data science is in the real world. So it's important to take these concepts seriously and work hard to understand them. So re-identification, privacy, you might strip names, other personal information might be stripped out of the data you're dealing with. But the network shape, the connections you end up retaining, can still be unique. So structural fingerprints can sometimes relink people to external data sets. You can also be able to relink you just generally. So even if you are browsing the web and you set your settings to not store cookies that are not necessary, and you use a proxy and you use a VPN that also hides your location, and you take all the regular steps that you're supposed to take, sometimes just by your mere browsing habits and the presence of some code on some websites, even if you're trying to be totally anonymous, you can be re-identified by your browsing habits alone. And these browsing habits basically connect you, the user, to all the websites you're connecting to, your history. So anyway, the graphical understructure of relationships between you and what you browse on the web, and you and what purchases you make, and et cetera, are not as anonymous as you might think. The graph itself can re-identify you. If edges represent friendships, they could also represent romantic partners, or medical referrals, or maybe activist ties. This is increasingly important in today's world. People are being re-identified if they happen to associate with groups that certain governments don't like. So visualizing these, publishing these can put people at risk. If somehow it's revealed that patient X was referred to an oncologist, then there's a good sign that they might be at risk of cancer, and that could be used for nefarious purposes. And then power and influence. If you can identify that some nodes are actually central hubs or highly influential, so there might be a lot of directed edges that point towards them. These might represent X follows Y relationships, and we're talking about node Y, which has a high in degree, a high number of other nodes that connect to it. Then those nodes might be targeted for ads or policing or harassment. And this is also something that we see happening a lot in the real world, where influencers are being repurposed to push political agendas. And if you misinterpret centrality or clustering in ways that are inappropriate, this can amplify existing inequalities, which we're always interested in trying to correct. So there's various mitigations. You can think before drawing your graph, certainly think before applying statistical methods to it. You can aggregate when possible, so you might if you have highly cliquey regions of the graph, you might even merge those nodes into single nodes. So these individual people is now going to be represented by this one node that represents all of them. And we've kind of removed a little bit of personal information in that way. There's various methods for doing that, which I'm not linking to right now, but this is more of a security question. And then, generally, this is something that I keep on repeating, you're going to have to perform documentation, perform write-ups, and communicate your findings to your stakeholders. Always, you have to be able to specify how your network was constructed, what assumptions you're making, why the statistics you're computing on these graphs are appropriate, and then what limitations or risks remain, right? It's always important to highlight any kind of uncertainty that might exist. Graphs show up all the time in computer science and data science and machine learning. Search and recommendations, obviously, so web graphs. So if you happen to be interested in this one website, and this website is links to this other one, then you might also be interested in that other one. So the relationships between networks on the web can help you do search and recommend, say, products, or recommend people who are very similar to you in social media websites. All this information can come to you from the kind of statistics and connectivity that exists between network representations. Epidemiology is more or less the study of disease in public health, and the infrastructure that exists in a community can help model disease spread. So if you have the flight networks between cities, you might notice that there is an outbreak of a disease in one city, and that city has a ton of airport connections to the second city. Then this can help you modeling disease spread. If you have basically a network of cities described by the connectivity that they have in terms of the infrastructure, like the transportation infrastructure, then you might be able to estimate how long it's going to take for a disease to spread to the cities in this graph. If you have power grids and you want to make sure that the residents of your city are not going to be affected by power outages, then the overall degree of the connectivity of individual households or regions within a city can be important. If you have one region which is only connected by one line, its degree is 1, and that line goes down, then everyone with degree 1 will be affected. You want to avoid that, so you might want to increase the connectivity in your power grid, and so on and so on. I'll point out that we're only really touching the surface in machine learning in this course. Machine learning is one of the most important and, in fact, impactful sciences that exist today. There is a form of neural network that is explicitly based on graphs. We just had a paper accepted this morning for publication that uses graph neural networks derived from transformer neural networks, but solve a lot of problems of the latter. So graph neural networks are an active area of research in deep machine learning. So for now, we're not going to need these details, but just to highlight that we're just kind of touching on this and then moving on in this course with many different topics. But graphs are keep on coming up over and over again, and they're important to start to learn about. Here are your quick checks as usual, and also as usual, it's been a pleasure. Thanks, and see you next time.